Okay, so this is 3 quantum states, psi1, psi2, psi3, and it says use the bracket notation, not the matrix notation, because remember, we can do all this in matrix notation. Griffith actually uses the matrix notation in his book for the most part. This guy uses kind of both, but more like this notation because it's just more efficient. It's self-containing and it's more straightforward. Sort of more straightforward. The algebra just tends to be less cumbersome with the bracket notations. Dirac introduced this notation, I think, to quantum mechanics. Okay, so to solve these problems, note, okay, so this is what we spoke about, that if you have a system in the state up, spin up, then the expectation value in the spin up, or the probability that you will find the system in the spin up, will be in the spin up 100%. So that's why it's 1. Likewise for minus half, but plus minus is 0, because if you take a system that's known to be spin down, the probability or the likelihood that you will find it in the spin up is 0, because we know for a fact it's in the spin down. So that's why plus minus is 0. Okay, so we kind of covered that. So now it says for each of the psi i's above, meaning 1, 2, and 3, find the normalized vector phi I that's orthogonal to it. So when a vector is normalized and orthogonal, we call that orthonormal. Yeah, because wave functions tend to be orthonormal, the ones that are physically defined and meaningful. Okay, so you need to find what that is using the bracket notation, not the matrix notation. They're all the same, so why don't we just pick up 3 and do 3 of these 3? Because it kind of illustrates the point. Now, you know what to do, or let me actually give you a hint. First thing, when do we know that a vector is normalized? Right? Normalized means the psi equals 1, right? The integral of psi conjugate psi is 1. That's what normalized means. The integral of that from minus infinity to infinity is 1. So in bracket notation, we say psi, right? For a wave function is equal to 1. That just means, if you want to be more concrete about this, that just means when you take the integral from minus infinity to plus infinity of the conjugate of this wave function times the wave function itself, dv, that just means equal 1. That's what this statement means mathematically. And orthogonal just means it's 0. The answer is 0. So orthogonal means, if I say psi 1, psi 2, the answer here would be 0. Or let's just leave it with, yeah. That's what this means mathematically. Okay?
Oh, wait, I'm not connected to the team viewer.
Okay, you want to connect?
Yeah.
Maybe I could show you one and then you could do another one yourself. Let me give you the password.
You know what else happened? While I was there, thankfully I wasn't sleeping.
Got it? Okay, so we said, so here we have to find for part A, we have to find psi I, normalized vector phi I that's orthogonal to it. So it has to be normal and orthogonal. Okay, let's consider the third one. Let's work on the third one. Okay. Okay, so so this is gonna be phi 3. Okay, and in general it's gonna be an unknown, so consisting of two states, one spin up, okay, and one spin down. That's what these mean. And there's gonna be some multiplicative constants, let's call them doesn't matter what you call them, alpha and beta, that would actually normalize this, right? Because they don't necessarily have to be in the same proportion or in a we don't know what the proportion is between these two states. Okay, but we do know that it's orthogonal to psi 3. So that means their inner product will be 0. That we know that. So we know that phi 3 psi 3 is equal to 0. Okay, make sure you understand what's in chapter 1 kind of builds the road into these things much more extensively, so make sure you understand these basics, otherwise you're gonna be lost in future chapters if someone doesn't understand here what's happening. Okay, it builds up. Okay, so because they're orthogonal, this has to be 0, right? Okay, now remember, I named phi 3 to be a ket, right? And in my orthogonality relation, it's a bra. So I would have to take the conjugate of it, right? In other words, when I apply this now, it's gonna be phi 3. So this is gonna be, so you're gonna flip these. That's what I mean. And when you flip them, you take the complex conjugate of the constants, because those constants don't necessarily have to be real. Right? So in other words, what I'm saying, to evaluate this piece, the bra of that ket, okay, this is gonna become alpha star, and then you switch the bra to a ket, or sorry, the other way around, the ket to a bra. So this becomes like this. You understand? The first piece. Okay, plus I do the same thing on the second one. So this becomes beta complex, the complex conjugate of beta. And then I flip the ket into a bra. So this becomes like this. So this is my psi 3 in the bra notation. Okay? And we are multiplying this by the ket of psi 3. The ket of psi 3 stays the same, like given in the question, which is this here. So I could just copy that. So 1 over root 2 plus e I pi over 4 1 over root 2 in this notation. And this has to equal 0 due to orthogonality. Right? Now, remember how we multiply these, right? We already said this... Oops, sorry, I meant to use the highlighter. this, when it foils on this, you get 1. Okay? But when it foils on this, you get 0. Right? So then let's write the what we get from this then. So spin up, this is just gonna get us alpha star 1 over root 2, right? Plus same thing for the spin down. When it foils on the spin up, it's gonna be 0, and when it spins on the spin down, it's gonna be 1. You understand what we're doing? So this will be beta star e to the I pi over 4 1 over root 2, and this is equals 0. Okay, so I have two equations with two. I have one equation with two unknowns, so I need another equation. Where will that equation come from? From the fact that it's normalized. Normalization means the sum of the squares. Okay, if this needs to be normalized, okay, that means the sum of the squares of this and this has to equal 1. So that's my second equation. You understand? That came from the fact of taking the inner product of phi 3 by itself and then foiling the states. And when you foil the states, again, you're going to get spin up is 1, spin down is 1, spin down, and spin up will be zeros. So you will end up with the magnitude of alpha squared plus beta squared equals 1. Alrighty. Okay, so let's solve this last equation now. So I could move everything to the right here, or it doesn't matter. You know, this we just have two equations and two unknowns, so we just have to solve this. From here on, it's algebra. So so we have alpha star equals minus beta star, or beta complex, e to the I pi over 4. 1 over root 2, but I'm going to divide by 1 over root 2, so these guys go away. Right? Okay, and then notice if I square these, if I square both sides, I get, or not, sorry, not square, but technically taking the complex yeah, basically squaring. Yeah, no, squaring meaning I multiplied by its complex conjugate. Yeah, and then same thing on the other side. I would take minus beta star, and this is gonna be beta star beta, and then when so that's when I square them, and then when I square this, I also multiply it by its complex conjugate. What's the complex conjugate of e I pi over 4? E minus I pi over 4. Right? Okay, cool. So that means these two go away. and I get alpha square equal beta square. Okay, plug it into the first equation, plug it into 1. So we get 2 alpha squared equals 1. So that just means alpha is 1 over root 2. And since they're the same, right? Since they're the same, that means beta is equal to 1 over root 2. And so now that I found my alpha and beta, you just plug them in psi 3, and that's your answer. So psi 3 is 1 over root 2 plus, is it plus or minus? Plus 1 over root 2 e I pi over 4. You just plug them back into the original one. Minus half. So this psi 3 is guaranteed to be orthogonal to phi 3 is guaranteed to be orthogonal to psi 3, and it's also normalized. In other words, if you were to take the inner product of this with itself, you are guaranteed to get 1. Said differently, if you were to integrate this times its conjugate, or its conjugate times this, and integrate it from minus infinity to infinity, the answer should be 1. Physically speaking, meaning it guarantees that the probability, right, because psi squared is the probability density, so when you integrate on dv, that means the probability of finding the particle, whatever particle that this wave function is representing in that state, guaranteed to be somewhere for sure from minus infinity to infinity. The probability of that happening is 100%. That it's somewhere. We don't know where exactly, but we know it's there. Yeah, part B is for each psi I above, find the normalized vector. We did that. Find the inner product psi I psi j for j1, 2, 3. So that means it's very simple. It's actually sort of what we did. I don't know if we need to repeat that, but it's basically saying take the inner product psi I psi j, right? So psi I, let's take the third one, okay, and take the inner product of that with psi j, with j being 1, 2, 3. So you're gonna do psi 3 psi 1, right? Yeah, there's gonna be 6, basically psi 1, 1 psi 1, 2, right? Psi 1, 3, and then the same thing for 2, 1, 2, 2, 2, 3. So psi 2, psi 1. We don't have to do all of them because they're all the same, but let's just make a few quick observations. Psi 2, psi 2, and psi 2, psi 3. Right? And then same thing on 3, yeah? There's going to be a total of 9. Psi 3, psi 1, psi 3, psi 2, and psi 3, psi 3. Let's make a few observations. What do you think the answer for this is? That's gonna be 1 because this is an normalized wave function. You understand?
Yeah.
And same thing for this. Psi 2, 2. 1. Psi 3, 3. It's gonna be 1.
Right.
Okay, how about psi 1, 2? What about, let's change the color here. What about this? Is this going, what do you think this will be? Is it gonna be 0? No, not necessarily, because we don't know if these are orthonormal eigenfunctions. The question didn't say that. If they were orthogonal, then yes, then the answer would be 0. But they don't have to be 0.
Right. Okay.
But what do you think the relationship will be between this psi 1, 2 and psi 2, 1? Well, think about it. All you're doing is switching the bra to a ket and the ket to a bra for on each one of them. So and when you do that, you take the complex conjugate of the multiplier. So in other words, what you're doing is you're switching between the real and the complex. So they're going to be complex conjugates of each other. You understand what I'm saying? So psi 2, psi 1, if you were to take the complex conjugate of this, you will get psi 1, psi 2. So in a test situation, you don't have to do them both. If you know one, to get to the other, you just complex conjugate the answer. So let's say if one of them turned out to be 5 minus 2i, the other one will be 5 plus 2i. You understand?
Right.
And the same exact argument applies between psi 1, 3 and psi 3, 1. And the same argument applies between psi 2, 3 and psi 3, 2. So you could see that this matrix of different inner products between wave functions is actually a neat matrix. We'll talk about that more as we roll through the class, because it has some interesting implications. Did you have any questions on this problem? 1, 2. You know how to normalize and take inner products now? I mean, we kind of did take an inner product on the first question, on the part A. That's why I didn't do any of those. But I just wanted to show you that.
Right, yeah, the normalizing is basically multiplying by the complex conjugate.
Yeah.
And what was the inner product? Was that Was that the diagonal?
The inner product calculus speaking, I wrote it here. Look, it means, you see this? The integral of psi conjugate psi dv equals 1. This is the same thing as this. It's just a more convenient notation that they use. So they don't have to keep writing integrals and dv, and then the algebra gets tedious.
Right.
But these,
integrating complex conjugates.
yeah, these two statements mean the same thing. Okay? It means that the probability of finding the particle has to be 100% somewhere between minus infinity and infinity. It's there somewhere. And the probability of finding it is 1. So that's the inner product. That's mathematically, another mathematical way to express it is to say inner product of bra of psi with the ket of psi equals 1. Okay?